Welcome back, and in this video we'll be talking about the square root function. So we're going to be interested in looking at a function and we want to see how we can sketch this using some techniques over here. Now the idea is that we want the expression of our square root function to look like this. So we're going to need x by itself, so we're going to be making use of the linear x rule again, and we want to observe the translations as well as the dilations. So the a value right in front is going to represent the dilation away from the x-axis. So remember, we're just looking at the size of a. The coefficient outside of the x minus h, b, is going to represent the dilation away from the y-axis. But remember, whenever we're dealing with the dilation away from the y-axis, so we're moving outwards, we're going to be taking the reciprocal of the magnitude of b. So 1 over b magnitude. For the translations, simply look at the h and k values. Just remember that h is negative here. So this means that if you have x minus 2, you're going to have a positive 2 value for your translation in the x direction. Translation y direction, relatively simple. As usual, we just look at the constant at the front and moves up or down according to that constant. And the reason why we look at the size of a and b is because the negative just represents the reflection in either axis. So if a is negative, we're flipping it upside down, reflecting in the x-axis. If b is negative, we're reflecting in the y-axis. So we're going to be mirroring everything in the vertical axis. And here's a quick summary of all the reflections that you can have. So ideally, your square root function is going to start at 0, 0. And that's why we look at translations so closely, because we're always going to be translating this endpoint, which is at 0, 0. And we're going to be translating this endpoint and then looking at the reflection. Over here, in the first quadrant, a and b are both positive. We want to reflect in the x-axis, flipping it upside down. We need only a to be negative. Flipping it to the other side, in the y-axis, b has to be negative. And of course, in this bottom left quadrant, both a and b have to be negative for that to happen. Okay, so over here, so if you want to attempt these problems before we get into the work solution, feel free to try and do it now. Pause the video. Otherwise, I'll go through these right now. Okay, so in here, we've got this expression over here. Now, is it in the right form? Seems like it, right? The coefficient of x is by itself, and we clearly have our k and a values on the outside. So that seems okay. Now let's list all the transformations we have. So we have dilation away from the x-axis of 2, looking at this a value. Translation in the x-axis, so horizontal translation is positive 3. Vertical translation is 1. Okay, so from here I like to plot the endpoint at the very least, and then have a look, or a quick preview of what kind of graph I'm drawing. So our endpoint is going to be at 3, 1, because we're moving to the right by 3 units, moving up by 1 unit. Okay, and it seems like we don't have any reflections either, so our graph is going to look something like this. So we're going to go towards the top right direction. Just remember that with the square root functions, you're going to move horizontally substantially more than you move up. So the dominant direction is to the side. Okay, are we done? Well, this graph doesn't actually show us what the dilation is so far. Because what if this dilation was 10? You'd still have a similar looking graph if you don't have any scale on your y and x axis. How can we tell the audience of this graph what our dilation is? Well, whenever you want to talk about dilation, just try putting in another point, and that will tell you the whole story. Not lines, we're looking for second point. Okay, so in this case, try subbing in a value that makes your life very easy. So it has to be an x value greater than 3, and you want this square root to give you a simple looking answer. So I want the inside of my square root to be a square number. So I can either make it 1, 4, 9, etc. If I want to make it 1, I just have x equal to 4. When that happens, y is equal to 2. That whole square root now becomes 1 plus 1. So y is equal to 3. And so this point over here is 4, 3. And that second point tells us how much the graph is dilating away from the x-axis. Okay, so over here, a lot of negatives again, and the first thing we always want to notice is the coefficient of x, and it doesn't seem to be 1 over here, so we're going to use the lonely x rule. So just recall that what is lonely x rule? We want coefficient of x to be 1. So coefficient of x must be positive 1. And so we just need to do a little bit of manipulation here first. So let's rewrite our expression. Keep the negative at the front. To make negative 2x, we take a factor of negative 2 out. X is by itself now. Negative 2 times negative 2 is equal to 4. Remember the 3 on the outside. Okay, over here, a lot of negatives, but they do mean something to us. Negative out here. This one means, not that one. This tells us we have a reflection in the x-axis because our a value is negative 1 here. Our b value is negative 2. So we got a reflection in the y-axis. While we're on the topic of b, we know that the b value represents the dilation away from the y-axis. But recall that we're always taking the reciprocal of the size. It's 1 over whatever number is there, 1 over 2 in this case. Translations, we have 2 going to the right, and 3 going up. Okay, let's do a quick preview again, just to see what kind of points we're interested in. Okay, so we're going to be going to the right, going up. So that end point is going to be at 2, 2, 3. Okay, so since we're reflecting in the x and y axis, we need to be sloping down. Now, if we're sloping down to the bottom left, we don't know if we're going to go through either here or here. So that's why we need to work out the intercepts before we proceed. Just redraw all of this out. Okay, so x and y ends. Y ends, x is equal to 0. When x is equal to 0, we're going to have, just following the one at the top, I have root 4, or negative root 4, plus 3. So taking the negative solution of square root 4 here, so negative 2, plus 3 is 1. So we're going to have a coordinate at, should be a bit lower, okay. So 1, what an x ends, a little bit more algebra here to do, but nothing algebra can't solve. So y is equal to 0, so over here we're going to have 0 equal to negative 4 minus 2x plus 3. I'm going to take my square root to the other side and square both sides. So we have 4 minus 2x equal to 9. Take the 2x to the other side, 9 at the other side. So subtracting 9 from both sides gives us negative 5. Adding both sides by 2x gives us 2x on the right side. And so x is equal to negative 5 over 2. So x-intercept should be about negative 2.5 around here. So negative 5 on 2, 0, going to draw this above the x-axis since our line is going to go through that. And roughly draw a line which goes through all of these. And remember that these intercepts, as long as you have 2 points joining each other, that it already shows the dilation. So we don't need a second point or otherwise to show we have a dilation of half away from the y-axis.